Hello everyone, and welcome to this course on linear algebra for physicists. Whether you are a first year or second year undergraduate physics student, or simply someone interested in understanding the mathematics behind modern physics, this course is designed for you. Before we begin, I'd like to explain the philosophy behind the series. This is not a pure mathematics course. Our objective is not to become a mathematician specializing in abstract algebra or rigorous mathematical proofs. Instead, our goal is to acquire the mathematical tools necessary to understand the law of nature. Physics is built upon mathematics. Whenever we study motion, electricity, quantum mechanics, relativity, thermodynamics, or even computer simulations, mathematics becomes the language that allows us to describe physics reality. Throughout this course, we will focus on developing what I like to call a physicist mindset. A physicist approaches mathematics differently from a mathematician. Mathematicians often seek complete rigor, providing every theorem from the most fundamental axioms. Physicists certainly value rigor, but their primary objective is different. They want to understand physical systems. They want to recognize patterns. They want to know which mathematical tool applies to a given problem. And above all, they want to solve a real world problem efficiently. This is exactly what we will practice. Our objective is to build mathematical intuition and computational reflexes. Many technical mathematical details and lengthy proofs, while beautiful and important, are not always necessary for understanding physics. Whenever possible, we will emphasize its intuition, physical interpretation, and practical problem solving rather than abstract formalism. By the end of the series, you should not only know how to perform calculation, but also why those calculations are useful in physics. What is linear algebra? Linear algebra is one of the foundations of modern science. It studies mathematical objects such as vector spaces, matrices, linear transformation, eigenvalues, eigenvectors. Those concepts appear everywhere in physics. For example, in classical mechanics, vector describe forces, velocities, acceleration, and momentum. In electromagnetism, electric and magnetic fields are vector fields. In quantum mechanics, it is a state of physical system represented by vector living in abstract vector spaces. In computer graphics, every rotation and transformation of a three-dimensional object is described by matrices. Machine learning, artificial learning, engineering, robotics, and numerical simulations rely heavily on linear algebra. Understanding these objects opens the door to almost every modern branch of science. Chapter 1 Vector. Let's begin with the most fundamental object of the linear algebra, the vector. In physics, a vector represents a quantity possessing both magnitude and direction. Examples include displacement, velocity, acceleration, force, electric fields, magnetic field. And mathematically, a vector in two dimensions is written as the first component represents the horizontal coordinate. The second component represents the vertical coordinate in three dimensions. However, mathematics is not limited to three dimensions. Linear algebra allows us to work in spaces containing 100, 1,000, or even infinitely many dimensions. Although impossible to visualize directly, these higher dimensional vectors can still be manipulated mathematically. Why higher dimensions might matter? You may wonder, why will physicists study spaces that cannot be even visualized? The answer is simple. Nature itself often behaves as it lives in very high dimensional spaces. For example, the complete quantum state of a particle cannot usually be described by only three numbers. Instead, it belongs to a much larger mathematical space, such called a Hilbert space. Linear algebra provides the language necessary to study these systems. Vector spaces. A vector does not exist in isolation. Vectors belong to a mathematical structure called vector spaces. A vector space is simply a collection of vectors satisfying a few fundamental rules. Within a vector space, we can add a vector, multiply a vector by a number called scalars. For example, the operation stretches the vector without changing its direction. This simple operation allows us to describe incredibly complex physical systems. Basis vectors. One of the most important ideas in linear algebra is the concept of a basis. A basis is a minimal base set of vectors capable of generating every other vector in the space. For example, the standard basis in two dimensions is every vector into plane can be expressed as a combination of these two vectors. For example, changing the basis will often make complicated physical problems much easier. This idea will become extremely important later when we study the diagonalization. Chapter 3, Matrices. Matrices are a rectangular array of numbers. For example, at first glance, this may simply look like a table of numbers. However, matrices are much more than that. A matrix represents a transformation. It changes vectors. It can rotate them, stretch them, compress them, reflect them, or combine all of this in the operation simultaneously. Whenever we multiply a matrix by a vector, the matrix transforms that vector into a new one. This is the mathematical description of many physical processes. Physical interpretation. Suppose we have a vector describing the velocity of a particle. Applying a matrix could represent a rotation of a coordinate system, the formation of space, a change of the reference frame, or the evolution of physical system over time. Matrices therefore become mathematical machines that transform physical quantities. Chapter 4, Eigenvalues and Eigenvectors. We now arrive at one of the most important concepts in all physics. Some vectors possess a remarkable property. After being transformed of a matrix by a matrix, their direction remains unchanged. Only their length changes. Those spatial vectors are called eigenvectors. The scaling vector is called the eigenvalue mathematically. The simple equation has enormous consequences on throughout physics. Physical meaning, eigenvalues appear everywhere. In quantum physics, they represent measurable physical quantities such as energy, momentum, angular momentum. In mechanical engineering, they describe natural frequencies or vibration. In structural engineering, they determine whether a building remains stable. In electrical engineering, they describe resonant modes. Whenever a system possesses electrical behaviors, eigenvalues are usually involved. Diagonalization. Suppose a matrix is extremely complicated. Wouldn't it be nice if we could replace it with a much simpler one? This is exactly the purpose of diagonalization. If enough independent eigenvector exists, we can rewrite the matrix as where D is the diagonal matrix containing the eigenvalues, P contains eigenvectors. Why is it useful? Because diagonal matrices are incredibly easy to manipulate. Computing large powers, matrix exponential, or solving a system of differential equations become much simpler. Many advanced physics problems will almost impossible without diagonalization. Developing the physics mindset. As this course progresses, I encourage you not to memorize isolated formulas. Instead, try to recognize mathematical structures. Whenever you encounter a new physical problem, ask yourself, what kind of mathematical object am I looking at? Is it a vector? Is it matrix? Is it a symmetry? Can I change the basis? Can the matrix be diagonalized? These questions gradually become automatic. This is what distinguishes someone who performs calculation mechanically from someone who truly thinks like a physicist. Conclusion. In this first lesson, we introduced the main ideas behind linear algebra and explained why it plays such a central role in physics. Throughout this series, we'll progressively study vector spaces, linear independent spaces, matrix determinants, linear transformation, eigenvalues, eigenvector diagonalization. We will solve many exercises that the level expected in the undergraduate physics programs. Remember, our goal is not simply to manipulate symbols. Our goal is to understand the mathematical language through how physics describes the universe. Because mathematics is not just a collection of formulas. In this language, it is the language that allows to discover the hidden structure of nature. Thank you for watching, and I'll see you in the next lecture.